we just focus on moment about Z. Okay, so moment about, so stress in the X direction is equal to minus mz over izz multiplied by y. Okay, so we will have a distribution looking like this, right? We will have a distribution. So if this is my axis, right, just to remind you all, and then this is my vertical axis, right? So this is our stress X, and this is Y, right? So the most important thing is I want to show that you will have zero stress on the neutral axis. Okay, so if we're going to sketch the stress on the stress induced by mz, we just focus on mz for now, right? We are going to have okay. So if we were to look at this relative to our shaft, we know that element K is over here, and in this position over here, this is our element H, right? Okay, so that's why this is 0, right? Element H, due to the bending moment that we have seen, is going to be tensile. That's why it's going to be positive. So you have to remember how the normal stress is distributed due to bending moment. Okay, now moment about Z, the 150, let's focus on the 150. Okay, so the 150, okay, we are focusing on the 150 over here. Okay, the 150 will also induce an axial load P in the X direction, which is equal to 150 pounds. Okay, and the 150 pounds will be put on the centroid, pulling at 150, because over here is pulling at 150, so you have 150 over here pulling on the centroid. Okay, so this will cause element H will be positive, and element K will also be what? Positive. Okay, why is that? Because over here Px will induce a stress X is equal to Px over A. Okay, so this is due to what? Axial load. Now some of you might ask me, Eugene, why? Why the 150 will transfer down? Okay, the reason why it will transfer down, as you can remember, right, is due to what we have over here. Okay, so we learned this a while ago. So this is known as the loading is known as, if I'm going to recall, is known as eccentric. Okay, eccentric, symmetrical, bending. Right. So as you can see, so let's bring our figure over. I'm going to try to copy this over. So I want you all to be familiar to what we're looking at. Okay, so on the right is our structure. On the left is a theory where we have eccentric symmetrical bending. Okay, so this is eccentric. So we know that P prime, right? P prime will also induce an axial load known as F. Because at the end of the day, the formula used over here is stress X is equal to F divided by area minus by mz over izz multiplied by y. Okay. So we also have a moment over here, right? Why we have so the point of interest is point C down here. So we basically log point C. Okay. And we know that there's a distance over here known as D, right? So we know that mz is equal to what? Is equal to P prime multiplied by D. And that's the moment. Okay, so the moment relative to point C is going in this direction. So the counter moment will go opposite. Okay, so for our case over here, right, we have to, so what we have, the 150 will cause a moment due to a distance away from the centroid, which is 10 inches. And then the 150 will also induce a what? An axial load. Okay. So a lot of times students only think, oh, it's only induced a moment. You have to be really, really careful. Okay. So because the 150 is inducing a what? Eccentric symmetrical bending. Okay. Right. So now we have viewed this structure. Anything else to see? Nope. So what we have identified over here is we have identified two things, two important things. Okay, two things we have identified is that we have a moment in the z-axis, okay, and then we have a axial load of 150 pounds. Okay. Anyone, any questions so far? Are you okay?
I got a question.
Yes.
In the moment equation, y element h is positive.
Because it's tensile.
Oh, I see. Yeah, thank you.
Right?
Yeah.
The head of the moment vector is compression, the tail end is tensile. That's why it's positive. Okay. Right. So next, I'm going to again copy that small figure. Okay. So there's nothing else to analyze, right? Next, I'm going to pick a different point of viewing the structure now. So the next point we are going to look at is we are going to look at the exact plane. Okay. So I'm going to change this over here. So the next one is we are going to now view this. So this is our X. And this is our Z. And then using right hand rule, this is rotation by Y. Okay. So we are going to view this in a different view now. Right. So I'm going to draw the shaft or the element, the point of the main shaft, 2, 4, 6. Okay. And then we have a circle down here. Then immediately draw your elements, right? So we know that over here now, this is your element H. And then over here now, this is your element K, right? And then the next thing that we draw our centroid. It's important to put in your centroid, the green line, relative to the element of interest. Me? Can you hear me? Are you okay? Okay, because there's a message to say that there's something wrong with the with the Teams, but since you're back, okay. So we have a force over here at 200 pounds. And then we have a force over here. Now you can see the axial load, right? 150 pounds, right? But we already know the 150 pounds is going to induce a tensile stress. We know already, okay? Then you have 50 pounds. And then over here, we have 150 pounds. Okay. Right. So now we are going to look at forces in the Z direction. Okay. So forces in the Z direction. So you can say, okay, I'm going to follow the transformation. Positive is coming down. Okay. We're going to do forces. Go on. We're going to do, let me see. Okay, we are going to do forces positive. So forces, or we're going to do VZ. Okay. So any forces that is coming down. Okay. So remember, if the force, like over here, the 150 is parallel or is in line to the centroid, right? So this is in line to the centroid. So the 150 is in line with the centroid, right? Then it will induced a axial load. Whereas the 150, 50, and the 200 are not in line with the centroid, right? So they are going to induce shearing force. Okay, so that's why I wrote down here is what? Shear VZ. Okay, so coming down is positive. So it's 200 minus by 150 minus by 50. So VZ is equal to 0. Okay. Now, the interesting thing now comes to the what? To the moment. We know there will be a moment in the what? In the y direction. Why is there a moment? So relative to the element, we know that we have a perpendicular distance. We have perpendicular distance. So we know that the distance from here to here, right? We know this distance is 4 inch. We also know that this distance from here to here, this is what? 6 inches. So now we're going to take the moment, right? From the where? From the element. I repeat again, we're going to take the moment from the element. Okay. So now we do, I'm going to call anti-clockwise, which is positive. Okay. So moment in the y direction, which is equal. So what we are doing now is we are taking the moment at the elements, at element H and element K. I repeat again, we are taking, so for this case, I'm going to put bracket for over here, a moment from the elements, right? Because at the elements is we're going to assume that's where the point of interest, or sometimes is where maximum stress will occur, right? So now we have 150. Okay, we have 150 multiplied by 4 plus by 50 multiplied by 10 minus by 200 multiplied by 10. Okay. So now we add this up. Okay, so it's 150 times 150 times 4 plus by 50 times 10, 200 times 10 is equal to minus 900 pound inch. So what minus means is basically you just put equal to 900 pound inch. You just need to rotate the moment. So the moment is in the other direction. So from here, we know that this is the direction about moment. Okay, so this is the direction for moment in Y. Okay. So we know the head of the moment vector is compression. The tail end is what? Tensor. Okay. So from here, what we can say is element H is equal to 0 for the moment, and then we can say that element K is going to be what? Negative, because it's in what? Compression, right? Okay. So now a lot of times what students are confused about, I want you to focus on this, okay? In the previous view, right? In the previous, the 150 is parallel to the centroid. The 150 is parallel to the what? To the centroid, right? So when we specify moment about Z, right, is equal to 150 multiplied by what? Multiplied by 10. Okay, remember the 150 is parallel to the centroid. So the distance is, right, the distance to get the moment is between the applied force to the centroid, right? You can see where the 150 is parallel to the centroid, right? The distance is between, so the perpendicular distance, I'll put down here, the perpendicular distance is between the applied force to the centroid, okay? However, for this case, right, the applied force are what? Perpendicular to the where? To the centroid, right? So the for this view over here, the applied force